Hey guys, welcome back to Solitaire Spade Science. My name is Yuichi Greywright, and today I'm going to be teaching you guys about... What am I teaching you guys? I remember! Yeah! Today I'm going to be teaching you guys motion on a plane. Alright son, it's about time we had a talk.
About what?
It's about time we talked about scalars and vectors. Wait a sec. We first must discuss friction. All you need to know right now is that friction is the force keeping us from falling through the earth, and the force that makes it so that an object slows down as it, moves across rigid objects. So, and now we will be jump cutting to smooth draw. Boom. Smooth cuts, I guess. Oh, get rid of that. Okay, guys. So now we're going to be solving some problems, and for this you're going to need basic, geometry, trigonometry. So yeah. So the first thing we're going to do, we're going to have a problem in which we're going to have a triangle. Okay. And then we have a ball right here. Now we want to find out how fast the ball's going to be rolling down the hill. Okay? This might seem a little difficult to do at first, but once you know how to do it, it's actually quite simple. Okay, so first, all we have to do... Actually, I should probably talk about vectors and scalars first. Okay, so vector quantities have... Actually, I might have gone over this before, but oh well. Go away. So vectors have both magnitude and direction, and scalars have only a magnitude. So we can actually, so when we're graphing out a diagram, we would actually draw. We can draw the vector arrow. So yeah, we're gonna get into that a little bit more in depth later, but for right now, this is all you need. Okay, so so downwards, the downwards force. The first thing we're going to try to do is we're going to try to put in the vectors, the vector arrows for all the forces acting upon the ball. So 9.82. That's how fast the ball should be accelerating. That's what the unit vector is for the gravitational, force. Okay, so and then like I said before, I mentioned that friction keeps us from falling through the earth to the center. Okay, so there's gravity, and so it's actually pushing outwards toward us, and it's not just opposite of gravity, but it's just it's opposite to whatever object you're pulling on. So like for an example, friction will be pushing outwards like that. And we know from Newton's third law that every action has an equal and opposite reaction. So we can graph this down here. Okay? And look, we can form a triangle. Okay? So, trigonometry will apply here because, triangle. This is 90 degrees. Because friction always applies to, directly perpendicular to the plane you're on. So we're trying to find, and we also know from trigonometry that these two angles right here are parallel. Yeah, these two angles are indeed parallel. So, yeah. So, using that information, all we have to do is find for x down here, and then we can find for x over here. And because vectors, usually we'd be doing it for actual, measurable distance as the magnitude, but the magnitude can really be anything. It can be speed as well, or acceleration, and that's what we're going to be using this as. So, yeah, I forgot to mention that this is going to be 45 degrees. Okay? So we know from that this is also 45 degrees. Or not that. I don't know what I'm saying. This is 45 degrees. 45 degrees. Okay? Well, this is also 45 degrees because, 45 plus 45 is 90, plus 90 is 180. Yeah, so we have the 9.82, and if we want to solve this, and we know from basic trigonometry that we can use sine of 45 degrees is equal to opposite, so katoa, opposite, which is x, to this angle, over the hypotenuse, which is the 9.82. It's important to have the 9.82 meters per second in the hypotenuse, because if you didn't, like, for an example, if you didn't graph it like this from the ball, but instead you did it, as the whole ramp, and you graph 9.82 over here, then you'll get a larger number for the slope, and it would seem kind of like think about it logically. It'd be really kind of strange if there was a ball, it was traveling faster than it would fall otherwise if you were to just drop it. So yeah, this is not 9.8. Okay, probably just confusing you guys. I'll stop. So yeah, we would use this, and then we can take this over here. So 9.82 sine 45 is equal to x, and then you can use that. I already have this solved, but you use your calculator and you solve for that. Where did I put it? Crap, I didn't write it down. That's dumb of me. Okay, so I'm just gonna jump cut. So yeah, see you in a minute. Sorry guys, I was being dumb and didn't write down the answer. So I had to go recalculate it on my calculator, and I was too lazy to bring it up. So yeah, so basically, if you solve for this, x is going to be equal to 6.943788 meters per second squared, and that's how fast the ball's going to be accelerating down this hill. So yeah, you guys just solve that, or I guess I did, but now you guys know how to solve it. So yeah, that's the answer. This has been Yuichi Greywright, and I'm signing out.